Hey guys, I would rather spend our class time tomorrow experiencing Newton's laws than talking about them. So I've made this little video just to give you a quick lesson on the three laws of motion and some examples. And then that way tomorrow we can do demonstrations with our time. One thing I wanted to mention before we get started with each individual law is that Newton's laws come up a lot in sort of popular culture. For example, every action has an equal and opposite reaction is the way most people would say Newton's third law. There's nothing wrong in particular with that, but it's not precise enough for a good physics understanding of what Newton's laws are. For that, you need the word forces. In fact, I think Newton's laws of motion would have been better titled Newton's laws of forces, because the first law is about what if there's not a force, the second law is about what if there is a force, and the third law is about interacting forces. And in some of those situations, there is no motion. So I think it would be better to use the word force. When you're asked to describe Newton's laws of motion, and you will be, I would like for you to make sure you're including the parts about forces and not just the kind of popular language. It's okay to have that in your head, but speak more precisely when speaking scientifically. All right, so let's get started. Newton's first law says an object will persist in its state of motion in the absence of a net force. We should probably talk about two terms here. One is persist. If a teacher's ever called you persistent, that's sometimes a compliment. It means you just won't quit, right? You not doing very well on a test, but you're going to persist. You're going to figure out what you did, do it better next time because you're persistent. You're going to keep on going. Sometimes it might be a criticism. It might be, man, he persists in hitting the chair of the person in front of him, right? That's also persisting. Persist means to keep doing whatever it is you're doing, to stay the same. And then net force is something that's going to come up a ton. So a net force is actually the balance of forces on an object. It is very rare that there would be only one force on an object, or that there would be zero forces on an object. Most of the time, you're going to have several forces. So, for example, I am standing still right now while I'm talking to you. That doesn't mean there's no forces on me, because we know there's gravity on me. I'm standing here on planet Earth. But there's also the floor pushing back up with something called the normal force. By definition, normal force is the response of a surface perpendicular to whatever force is being put on it. So it's equal in magnitude, but opposite in direction. Therefore, I have no net force on me. Net would be what's left over. If the floor, let's say gravity was pulling down on me with 100 newtons of force, and the floor was pushing back up with 120 newtons of force, I would float off the ground because the floor would be pushing me up with a net force of 20 newtons. That's what net force means. It's the difference between the forces. This is going to come up a ton later, so you're going to want to know that. But Newton's first law specifically is about what if there is no net force? All the forces on an object are balanced. So, for example, consider the golf ball here sitting on this tee. Gravity is pulling down on the ball. The tee is pushing back up. That is two forces, but because they are equal in magnitude and opposite in direction, the net force is zero. Therefore, that golf ball is going to sit there forever unless a golfer comes up and swings at it. Like Garrett here. Garrett takes a good swing at this golf ball. Now it's going to accelerate. Okay, but that's Newton's second law, so I'm getting ahead of myself. But he has to apply a force in order for it to move. But then there are times where maybe something's already moving. Take, for example, the Voyager space probe pictured here. This was launched in the 70s, and it went out and it took pictures of many, many planets as it went by. When they launched it, they got it up to the speed they wanted it to go while still inside the spacecraft, because the spacecraft had a propulsion system, right? It could move, it could get up to speed by applying force. Then they let the probe go already at that speed, and it did not provide any further propulsion on its own. It just kept going and going and going and going, and as far as we know, it's still going and going and going. Unless an asteroid hits it or something, it will keep going forever. It passed Pluto a couple of years ago, and it's out in interstellar space now. So it's not sending us pictures anymore like it used to. That was only designed for a certain amount of time. The battery obviously has gone out long ago on that. But it didn't need any more propulsion because it was persisting at the speed it was already going. Now, Newton's second law is, what if there is a net force? What effect does that have? And it's stated this way: the acceleration of an object is directly proportional to the applied force, or the net force, on that object, and inversely proportional to the object's mass. This makes sense if you think about it, but let's look at some examples. Let's go back to Garrett hitting the golf ball. Golf balls are pretty small. I don't know how much their mass is, but it's not a huge mass. It's designed pretty perfectly to be hit by a golf club. And so the force applied to that will lead with a pretty strong acceleration. In fact, there's an equation for this that perfectly describes the relationship that I just told you in words. A equals F over m. Acceleration equals force over mass. So because the F, the force, is on the top of the fraction, it means it's directly proportional to the acceleration. The bigger the force, the bigger the acceleration. Because the m is in the denominator of the fraction, that means it is inversely proportional. The bigger the mass, the smaller the acceleration. So when Garrett hits a mass that's pretty small, well, it's going to accelerate pretty big. But let's say we replace that golf ball with a bowling ball. When Garrett hits it with the same amount of force, the bowling ball is going to have a very small acceleration. And in fact, Newton's third law might come back to bite Garrett and break his club or his hand or something. But again, I'm getting ahead of myself. The problem is that all the laws apply to everything. So it's hard to talk about them one at a time in isolation. But that increase in mass will decrease the acceleration. That increase in mass will decrease the acceleration. If you look at this spacecraft, this is actually a fictional spacecraft. You may recognize it from The Martian. We actually have a couple of options for sending people to Mars. One is what we currently do, or what we did when we went to the moon, which is to get a spacecraft up to speed quickly using a whole lot of fuel, and then drop the fuel tank, going that speed and continuing to go until we're taken over by the gravity of, well, back in the 60s and 70s, the moon, but now would be Mars. That is an option, but it requires a whole lot of spent fuel all at once and allows for very little change. The way they did it in Andy Weir's book, The Martian, which is not explained in the movie, is that they do a little bit of acceleration over the entire time. So you don't speed up all at once and then keep going using Newton's first law. You continue to apply a consistent but small force, and so you keep getting a consistent but small acceleration. But a small acceleration over the course of months becomes a very, very, very high speed. That is one of the things that's being researched, which is why Andy Weir chose to put it in his book. So if I want a small amount of acceleration, I can use a small force. If I want a big amount of acceleration, I have to use a big force. Really, those two things are both necessary when you're talking about Newton's second law. Newton's third law is, there's probably not just one force. What happens when there is an interaction of forces? You see they get more complex as you go. First law, no net force. Second law, a net force on one object. The third law is about interacting forces. What if they act on each other? So the statement is, when an object exerts a force on another object, the second object responds with equal force in the opposite direction. Mathematically, what that's going to look like is Newton's second law back to back. So if I have equal forces, I change the equation around from A equals F over m to say, well, if F is the same, how am I calculating F? That's going to be m times A, mass times acceleration. So if they're equal in magnitude but opposite in direction, I end up with an equation that looks like this. m1a1, right, 1 being the object, is equal to m2 times the negative of a2. We put the negative on the acceleration because it's a vector. And in this case, that negative sign is directional. You can't have a negative mass. That's not possible. But you can have a negative acceleration. In this case, it's not slowing down. It's directional. It's in the opposite direction. So you end up with mass 1 times acceleration 1 is responded to with mass 2 times the negative of acceleration 2. For example, when you are in a canoe and you want to move forward, you push the oars back. You're pushing back against the water. The water responds with an equal force in the opposite direction and pushes you forward. If the masses are similar, the accelerations will be similar. But if the masses are very different, then the acceleration's magnitudes will be very different. It's the force that's the same, not the motion, right? The force is what's equal in magnitude. So, for example, when the space shuttle launched, lots and lots and lots and lots and lots and lots of gases came out the end, right? Came out of the bottom of those fuel tanks. Compared to the mass of the ship, the mass of the gas was quite low. It's a lot of gas. It was tons. It was the hundreds of thousands of tons. But that weighed far less than the millions of pounds of space shuttles. And so as they came out, they were moving very, very fast. But they caused the shuttle to respond in the opposite direction with the same amount of force. That's what launched it. Well, that excessive weight of the shuttle caused there to be a very slow acceleration from it, right? So the M1 and the A1, in this case, you had a small m in the gases, but a very large A. And the shuttle itself was a large m, and so you had a very small A. Another way to think about this is the recoil on a gun. If you've ever shot a gun before, you know you've got to brace yourself. You've got to hold yourself in a certain position. If it's a shotgun or a rifle, you put it against your shoulder. And that is because a large increase in acceleration coming out of it is going to accelerate back the other direction. Now, compared to the bullet or the cartridge or the shot, the mass of the gun is very, very big, and the bullet is very, very small. So the acceleration of the gun is going to be a lot smaller. But it's not nothing. And so one of the reasons why you put it on your shoulder is so that you include the mass of your upper body in the recoil, which makes the acceleration less. Hopefully this makes sense. If it doesn't, ask me some questions tomorrow because I'll be happy to talk to you about them while we are experiencing them. But for now, this video is about 13 minutes long, so I need to get off of here. Have a good night, and I will talk to you tomorrow.